So I'll tell you a story that we have been working on with my collaborators, Damian de la Fuente, Nicolas Libedinsky, and David Plaza, all here from Chile. And yes, the idea is that we're going to mix Bruhat order with Ehrhart theory. I'm going to explain two results that we obtained recently, and basically, I will spend most of the time simply getting to the statement and showing you some interesting pictures. So the main thing is that we're going to talk about the Bruhat order, which is a partial order on the elements of an affine Weyl group. We will see examples in a second. And what we care about this poset are the sizes of intervals. So in general, you have two elements that are comparable. One is smaller than the other one. We can define always the interval, every element that lies between them. And I care about the size. Yesterday there was a talk about all the intervals, so all the pairs of elements such that one is smaller than the other one. So this is slightly different. I fix the two endpoints and I want to count how many elements do we have there. So in other words, I can restrict my poset to have like a minimum U and a maximum V, and I want to explore that poset, in particular the size. That's a very open-ended question. I think that, yeah, not a lot is known about these general intervals. We're going to focus today on intervals that are from the identity, because recall that this is a partial order on a group. So there is an identity element, and then we put on some extra element. But we will also see that even when one of the elements is the identity, the other one, it will have to be special for our results to hold. But this is the most typical shape, identity, comma, something. And the idea, the philosophy is that we are going to try to have this enumeration problem relate to Ehrhart theory, relate to lattice points in some polytope. So from this, we can say that the number of lattice points, so the size of this interval will be a polynomial. But this is only an idea, and it's hard to make precise, because the first thing that is very subtle is a polynomial in what? These are groups, so we will need to somehow involve parameters. Okay, so let's briefly recall what is the Bruhat order, although I guess most of the audience know, but let's do the case of the symmetric group specifically. So this is a partial order that is the easiest thing to me is to define it using the covering relation. So this will define only the Hasse diagram. And we're going to say that two permutations, U and W, are related if one can be obtained from the other one by a single transposition. So this is multiplying by a transposition that changes I and J. They don't have to be consecutive. It's not I and I plus 1, just any transposition. And importantly, the length of W increase by 1. So what is the length? Very naively, we can simply say that is the number of inversions. So these are pairs of integers that are swapped if we think of the element of the symmetric group as a bijective function. Okay. So this is how this thing looks for n equals 3. So we have 6 permutations, and this is the Hasse diagram. So these are all the covariant relations that we get there. So this is the poset this poset is graded, and is graded by length. So in this case, it's graded by the number of inversions. You see 0 inversions, then 1, 2, and the top element will have 3 inversions. No, 1, 2, 3. Okay, this is very classical. Now, why this matters is, well, this definition is not very practical, maybe. I'm only defining the covariant relation. So if you want to know whether one element is smaller than another one, you will have to, according to this definition, construct a chain and decide if there is such a chain or not. There are many more equivalent definitions that are of importance from a practical point of view and a theoretical point of view. For example, if you are into this complexity and chart P and combinatorial interpretations, yes, there is a polynomial test to check quickly whether U is smaller than W. There is a form of this called the tableau criterion. In some places, it's called the Ehrenmann's criterion. This is in Björn Brent's book and in many other places. And this uses some like quadratic number of comparisons in some array that you have to build. So there are other equivalences that are practical. There are also equivalences that are of theoretical importance, because this also this also arises in algebraic geometry, in enumerative geometry, when you have Schubert cells. The Schubert cells are indexed by permutations, and containment of the Schubert cells is the Bruhat order. And there is a lot of theory about the Bruhat order that come from algebraic geometry and from so more abstract things that we are not going to talk about today. We are going to be in the combinatorial realm, but also know that the famous Kasdan-Lustig polynomials are some polynomials that are defined on Bruhat intervals. And also I want to mention there's 10 years ago, there is this work by Zuckerman and Williams where they define and study Bruhat interval polytopes. So you have a whole interval, so you have two permutations, one is smaller than the other one. You consider all permutations that are in between, and you take the convex hull of them, not of all permutations, that would be the permutohedron. So the Bruhat interval polytopes are well behaved, and there is a lot of information about them, and I think they will be mentioned in the last talk of the day. So I just wanted to mention that here. And just to mention some extra results, is known, so the size of the intervals, not much is known, but one thing that was an object of interest is the rank sequence. So this poset is graded, so there are some elements of rank 0, of rank 1, of rank 2. These are simply a sequence of integers describing how many elements we have in each level. There was some interest on the ranks of Bruhat intervals, and there is a result that is actually much more sophisticated and complicated. But in this study, let's say that they prove, among other things, that this rank sequence for intervals that look like the identity comma some element, any element, it increases at the beginning. Okay, so then it does other things and more is known, but for now let me just say this. They prove it in a more abstract setting of a crystallographic Coxeter group, which will include the affine Weyl groups that I mentioned in the title. So this is something that is known, and these techniques are coming more from algebraic geometry, but today we're going to keep it more combinatorial. Okay, so that's the general question. Which this will be like an open-ended question. Like, okay, we are doing enumerative combinatorics, maybe some algebraic combinatorics because this is related to algebra. And are there pairs for which we have good enumerative result, like some formula that is close somehow? Even when U is the identity, I don't know. I don't know of many of these examples where there is like a precise enumeration. I really don't know. So this is an open-ended question, whether is there anything interesting to say. Now for permutation, this is a finite group. So, okay, so everything here is finite. Now let's go to affine Weyl groups, which will be the infinite version. And everything I'm going to say, I'm going to do all of my pictures with the affine symmetric group of like rank 2. And I will explain what generalizes and what doesn't generalize. So for now, we take some two-dimensional space and some lines, and we're going to consider the reflection group generated by those lines. It looks something like this. So in dimension 2, we can take an equilateral triangle. Now, this is a lie. In higher dimension, you don't take an equilateral simplex, regular simplex. But in dimension 2, and for the sake of these pictures, you can take any equilateral triangle and have extend its three sides, and equally do parallel translate in all three directions. So you will get a triangular grid. Okay. The group, so what is the group? The group is generated, the group is infinite, and is generated by all the reflection among the lines. So the group has reflections, it will have translations, and it will also have some rotations if you do, for example, reflections that intersect. So this gives you a triangular grid. And what is very common here is that this group acts freely and transitively on these triangles. So we can simply identify the group with the set of triangles, and these are the alcoves that give name to the conference. So we can choose any of these alcoves. There is nothing special. We're going to choose one and say that's the identity, and any other alcove is going to represent a unique element. Which element? Well, the element, the element of the group that takes, there is a unique element that will take this chamber, let's call it the fundamental alcove, the E, the identity to W. is taken by some composition of reflections that give you an element of the group. So we identify the triangle, the alcove, with the element. So from here on, I'm going to confuse alcoves with elements. Each alcove is an element, each little triangle is an element pointing up or pointing down. I mark these three lines. These three lines are special. Basically, these are these three lines. In this particular example, I just want to mark them because it splits the whole plane in six pieces, and the piece that is on the top is going to be called the dominant chamber. There are some different conventions on what is the dominant chamber, but for the pictures today, when I say dominant, I mean anything that is here on the top infinite cone that spans to where W is a dominant element, let's call it here. Also, this group is infinite. There are infinitely many alcoves. But if I look at here, if I declare this to be the origin, all of the alcoves touching the origin, it has a Weyl finite group. And in this case, it will be the six permutation. So S3 in this case. So we can identify this with a group of permutations of three elements. Okay? So now, what is the Bruhat order here? So I'm not comparing elements abstractly, but now I'm going to compare alcoves. I'm going to compare two triangles. I need to know when one triangle is smaller than the other one. And okay, so very similar to the previous one, I'm going only to describe the covering relations. W covers U if I can multiply, like, is U times a single reflection, or the reflections that define the whole group. That is the right generalization of any transposition. And the length increased by 1. Now, what is length in this case is simply the number of lines that separate this from the identity. Okay, so in this case, I have some element W, I have the identity, and there are some lines, a finite number of lines, that separate the identity from W, and that's going to be the length of W. Okay, so this mimics the previous Bruhat order in the permutation. Now this is an infinite group, but the order is defined in a similar way. Okay, so that's the main problem. I want to have Bruhat intervals in this setting. Now, this is what we want to do. What is the size of these Bruhat intervals? And the main thing is that they look polytopic. And what do I mean by this? So I have to share something else. So let me share you a shout out to this website. So there is this website by Joel Gibson, very helpful for a lot of things, lots of mathematics software. Let's go to Lee visualization. And there is even more, so many toys to play around. So let's go to only one of them. And right, so we are here. And my convention is this is the identity. So no, I want the identity to be on the bottom. Let's put the identity here. Okay, and this is type A2, let's say labels. No, this is okay. And shade. Now let's do it with the Bruhat order. So what is this program going to do is the following. This thing, I will going to put an alcove. Remember that an alcove is an element, and this thing will shade the whole interval between the identity and the element. Okay, this is pretty cool. You can simply play with this. And at some point, let me see if I can zoom. Oh, yeah, I cannot zoom. Oh, sorry. Ah. Okay, good. So here you can start seeing like this thing looks like an hexagon. This thing looks like a permutohedron. When you play with this, you realize like this feels like a polytope. It is not really a polytope. You know, there are some Hades, some spikes at the end, but morally it feels like yes, you somehow have a polytope here. You just have to define it properly. Okay, and you can see that there are two cases. Now the good thing is that you can play with, I mean, I was just mentioning the A2 case, you can also play with B2, and it also looks polytopic. Some elements more than others. You can play with this. There is also the G2. This is the one that appears in the website. So in the website, you have this crazy group. But again, it's a finite reflection group. Is generated by all reflections in these lines. And this is like an opposite. And this also looks polytopic. But it's complicated. You see, like here, it's like missing something. This is like a honest to God polytope. But there are some other examples, like something like this and so on. So this is what we want to explore. for arbitrary affine Weyl groups, how can I like make sense that this thing is somehow a polytope? So let's stay in A2. And we will distinguish two cases. So triangle looking up and triangle looking down. Okay, so this is, I mean, there is a lot to play here. And by the way, I don't have time, but let me, for more promotion, you can also have the right week order, not that interesting, and the left week order, interesting, but less polytopic, full of holes. Okay, so that was the software demonstration. That is not even mine. And let me go back to the view. Okay, so they look polytopic, but now we have to make that precise. Okay, so first of all, so we have two results, and one is that if the triangle was pointing down, so something like this, then the whole interval can be tiled with hexagons. So I tile with hexagons, and then the enumeration becomes how many hexagons times 6. So I will count the number of hexagons and multiply times 6. And to count the number of hexagons, it feels like I have like a lattice here. And these yellow dots are the lattice, and they feel like the root lattice. So if you know what is the root lattice, there is a bit of a problem, because I mean, usually this point here will be the zero, the identity, and this is not containing that. So it's a translate of a lattice, but still it morally looks like a lattice, and it looks like I'm counting the yellow points, which they seem to be points in a polytope. So in what polytope? So it seems that I'm counting. I have this point, and I have the orbit, that's the permutohedron. So I will have this point here, and let the finite Weyl group act on it. So in this case, the six permutation will act with these 6 reflections. I get 6 points, and I take the convex hole, and I count how many points in this lattice I catch with this. Now, if I want to give coordinates to this, because again, these are groups, these are elements of a group or alcoves. Now I need to give coordinates. I can give coordinates in the so-called weight lattice. So I can say the coordinate of this guy is 1, 2, 3, and 1, 2. Somehow I can say that this is the point 3, 2 that corresponds to 3, 2 in some bases. And that point is the one that I'm taking the convex hull of its orbit. Okay, so this is what we make precise. First theorem. This is true for any affine Weyl group W. So there's going to be a typo here. So this is the affine Weyl group W. It can be anything. And for certain elements. Now the definition of the element is here, but in this picture, the thing is I can only do this for elements in the dominant part. Being dominant is not that important, but in order for this tile to work, I need the triangle to be pointing down in this case. In general, we need some definition. That's a little technical, but for some elements that can be defined in any affine Weyl group, it turns out that the size of the Bruhat interval is a polynomial in lambda. Why? Because it becomes the number of integer points in certain permutohedron. So we will take this point lambda. Let this should be the finite. So we have an affine Weyl group which can be infinite, but there is always a finite group associated to it. So there is an F missing here. This will be a polytope. In type A, this is the permutohedron. And we are simply counting the number of integer points in certain of lattice points with respect to certain lattice. So this thing is a polynomial. And moreover, because of Ehrhart theory, it's related to the volume. So the volume of that polytope is also a polynomial on the lambda entries and on the lambda coordinates, and that volume is like the top degree. So we have like, this is to a first degree approximation, the size of the Bruhat interval plus some lower order terms. Okay, so this is something that we prove. Let me repeat, for any affine Weyl group, but the drawback is that it can only be for certain elements that are defined here. So we take the longest in the affine Weyl group. In the finite, we take the longest element, so the opposite here, and we have to translate that guy. So we translate that guy. In this case, it will be all triangle that point downward. Okay, so we were trying to generalize this theorem. What can I say if this is a different element? So what can I say in my two-dimensional case if I am not a triangle looking down, maybe a triangle looking up? So now I have to do a different tiling. Maybe this picture is not that clear, but the tiling, now I cannot use hexagons. I mean, hexagons will approximate the picture, but they are not going to fit because of the spikes. So what we realized is that we have to change the hexagons by something called paper boats. So we call it the paper boat paper. These boats are going to tile like the inner part. And this is where some details get complicated, and I don't want to give you all the specific definitions, but we define some boat, some paper boat that it looks like this, and when you are deep inside, then these are all boats. And the complicated part is that as you get close to the walls, these things get deformed. Now, one of the reasons why we are only doing the dominant part is because in practice, you are working with Bruhat order, and we need criterions to compare two alcoves, and we have some criterions, but these criterions are better, are smoother, are easier if I'm always comparing in the dominant chamber. So we restrict to the dominant chamber. We are only tile the dominant chamber, and then whatever we get here, we multiply times 6. It's not that big of a deal, but the problem is that it doesn't behave. I mean, near the boundary, things get deformed, but deep inside, they are all paper boats, the blue ones. Okay. So now what will be the count? The counting is, okay, just give me the number of paper boats. So give me the number of tiles. But the big problem is that the tiles have different sizes. Okay. So the boat is giving me 6, but these yellow ones are giving me 7, and the red ones are giving me 4. So still it looks like a lattice point count. So I kind of like define some polyhedral regions, and I'm counting points in certain lattice that is related to the root lattice. And when I count these points, now I have to weight them. And this makes things more complicated, but still, you can use Ehrhart theory for this. You're doing a decomposition. This guy, now I have to, all of the blue points count for 6. The yellow points count for 7. Same for this one. And this region will contribute 4, 4. And there is a weird one here being 5, which is the last cover in here. Okay. So things get more complicated, but still. And also these polyhedra are no longer, I mean, they don't have to be, they are only rational, not lattice polytopes when we are defining all of these things. So this is the theorem that we can get. Context. This is for the affine symmetric group. So affine type A. This is important to remark because we don't have it in general. In the previous case, it was in general. In this case, we don't have it in general. And why not? For the experts, one thing that is true in type A that is not true in other types is that alcoves, the vertices of any alcove, represent all classes of the weight lattice modulo the root lattice. Like all the equivalence classes between these two lattices. And this is not true for general affine Weyl groups, where this quotient may be 2. For example, in type B, and you have like more than 2 vertices in an alcove. And this is a technical, in our argument, this is a technical problem. So only for type A, so that's good. We are still in the triangles, in the triangular grid. But now we can do it for every element of the dominant region. We can prove that the size of the interval that go from the identity to W is a quasi-polynomial. We have to go to quasi-polynomial because the polytopes involved are not rational anymore, but still some quasi-polynomial. I'll say more about that in a second. And yes, in lambda. Now, what is lambda? Lambda is complicated. I need to give coordinates to this thing. So for example, when I was doing the tiling of this element, I need to have some lambda, and this I'm going to call coordinate 9,2. This is a little convoluted, but basically we take a fundamental parallelogram, and everyone lives in a translation of this fundamental parallelogram. So this element, the purple one, I have to take the fundamental parallelogram and translate by 9,2. So I'm going to use, like, that's going to be my parametrization. 9,2, so when I say quasi-polynomial, I mean I have to plug in the parameters 9 and 2. So that's how you get the parameters. What is a quasi-polynomial? There's not a lot of time to say this, but something that has cases. So for example, the floor of n halves has like 2 formulas. It's depending on whether you're even or odd. And I cannot say more, but I really recommend this survey by Kevin Woods, the unreasonable the unreasonable appearance of the quasi-polynomials. They appear in a lot of places, so this is another surprising, or maybe not so surprising, scenario where they arrive. So finally, our theorem is, okay, it's true there is a quasi-polynomial, But we can say more. It turns out that this is something that has cases and whatnot, although we can explain the top degree part. The top homogeneous part doesn't have any cases. The top homogeneous part is an honest polynomial and is again the volume of the corresponding polytope, the corresponding permutohedron that we get by applying lambda and taking the convex hull of certain orbit. So this formula still looks like is the volume plus some lower order term. So still the volume of a polytope approximates the size of the interval really well. These lower order terms are things that right now we really have not too much control over, but it's kind of nice to know that at least the largest degree is controlled by the volume of the polytope, just as in the previous case. And this sounds kind of like, okay, we use Ehrhart theory, and it's known that the top part is the volume, but still there is something else behind all of these things, and something key is that these paper boats that we define and the hexagons have the same number of alcoves, 6. So somehow generically things count for 6. And this is something that is true in higher dimension, but takes a while to prove that whatever our definition of paper boat is, it does have n factorial elements. So that's kind of important to prove this theorem. And but that's it. That's where we are. This theorem is also very hard to we don't know what happens in other. It's not that clear. It's not that transparent. If it's not dominant, if we start in another chamber, it's not very well understood. And all of these results are with the identity below. We are still far from being able to put any U here. So there is still a lot to do in these directions. And that's all I wanted to say. Thank you.
All right. Thank you, Federico, for this great talk. Do we have any question from the audience? Maybe I can start. So you say it's hard to get to non-initial intervals, but can you say something more on what is the main obstruction?
So naturally, a non-initial interval is the intersection of everything that is lower than the lower one. So that's one case that we already have, intersected with things that are, the other thing is like a star. You have to be not greater than the lowest one, something like that. So any interval is the intersection of a principal going down and a principal going up.
Yes.
The principal going up, when you picture it, it looks like a star. When I say that things look polytopy, that one doesn't look polytopy, but still, it looks starry.
I see. Okay, thanks. There's a question in the chat. Does anything nice happen if you count the number of these intervals of a given size, or even better, make the generating function of these intervals counted by size?
I haven't tried, and that will be cool. Yes, no, maybe something could happen.
Okay, and then another question. Liz, is that a raised hand?
Yes.
Okay, so we'll go with you.
I was just wondering if you could say more about why other Weyl chambers are harder to handle.
You mean not the top one? Because okay, let me the criterion that we use to decide when an alcove is smaller than another one, that criterion is general, but is simpler when everything is in the dominant chamber. But I want to be more explicit about something. In particular, there is something called, I don't know how people call it, some walls. Anything that is, let me go way back. Anything that is close to these lines, close to these red lines, but on this side, they behave really differently, kind of a mysterious. But there are 3 walls here. This one, like the walls that like parallel translations of the identity, they behave slightly different. They just do. I don't have any good explanation for that.
And I get there's another question in the chat from Mohammed. How did you come about the boat structure? It's slightly surprising given its non-convex shape.
Yes, I'm hiding the definition, but when you look at the definition, it's not that surprising. It's not looking at the picture. It's thinking, the definition is something about, we need all elements that are smaller than you, but not smaller than some of your translate by a root vector, something like that. So it's like you have to be below, but not below your neighbors in the root in the root direction, something like that. When you think of it that way, it's not that crazy. So yes, we were not really staring at the picture. We were staring at the proof and the technical things that we needed. Yeah, okay, that will be a good insight, like Voronoi style.
I have a question.
Yes.
Yes, I was wondering, do you have any ideas of, say, how your results would look if instead of the usual Bruhat order, you considered variants, such as there have been recently published variants on higher Bruhat orders of types B and C, and there's even a variant by Weyl et al. On something that is a hybrid of something that is quote unquote between the weak order on permutations and admits a Bruhat order as a refinement.
Okay, I have not thought about that. That will be cool. I don't have a feeling for this high. I know it exists, but I don't have a feeling for the higher Bruhat order. However, experimenting with the software that I show, if you go to something more basic like the Bruhat order that they call the strong order, you can also use left and weak. And if you play with these pictures, it looks less interesting. Yeah, like that. That was the picture that I was showing. Like at least at that level of using those two posets, it's not that interesting. But still, I don't know if there is I don't know of anything written. But it looks simpler. For the higher Bruhat, I really don't know. That's a good